All right, so let's get started. So the plan today is to finish off the physical layer and then start to talk a little bit about something called error detection, which is a crucial part of the data link layer, as we will see later on. We will, some mop-up of the physical layer and then go on to new things. So let's get started. We talked extensively about this. So here we have a pulse amplitude modulation transmission scheme. And this is the workhorse of physical layer, and many physical layers can be mapped onto structures like this. So basically we have some bits. We have some bits that we would like to transmit. So input to the left is bits, and output to the right are decisions on these bits. And we transmit the bits in blocks, becoming symbols. And just before the end of the receiver, we have decisions on the symbols. So we have data in the form of bits and data in form of symbols. And we define something called the symbol error probability, which is the probability that the decision on a symbol, A hat, is not equal to what was transmitted, A. And we define also something called bit error probability, which is the probability that the decision on the ith bit, bi hat, is not equal bi. And of course we would like these error probabilities to be small in order to have a good functioning system. They can never become zero, however. So this is something that we need somehow to deal with. And in our protocol stack we will do this mainly on the data link layer, but also on other layers. And we will see how to do that a little bit later. In computing the error probability, it turns out that the energy per symbol is a crucial parameter. So the energy per symbol is the, if one looks at the energy in the transmitted signal for many symbols, take that total energy and divide with the number of symbols we have transmitted, then we get the symbol energy. And one can show that the symbol energy can be written as a product of two things, EA and EH, where EA is something we call the constellation energy, and EH is the energy of the pulse shape that we use. And if we look at the constellation energy, is the expected value of the magnitude square of the amplitudes that can be transmitted. Because these amplitudes here, AK, can take on different values. AK is a member of the symbol alphabet, which consists of the amplitude A1, A2, up to AN, like this. And if we take the average of all of these, then we get the constellation energy. And the last inequality here holds when the bits that we are transmitting are independent and equally likely. Equally likely means that this bit has the same probability of being a 0 as a 1, so 1/2 in that case. Independent means that consecutive bits here are statistically independent of each other. And that's a standard assumption that we use. Okay, now this symbol energy here turns out to be crucial when we calculate the symbol error probability. And it's related to the transmit power, P, through this general rule that power is equal to energy times rate. So we can calculate the transmit power as the product between the symbol energy and the symbol rate, or the bit energy and the bit rate. Okay. And what we did last week is, not last week, last time we saw each other, was to calculate the symbol error probability for M-Mary PAM when we have equidistant constellation. So a constellation where points are centered around 0 and then spaced evenly on the axis like this. And if you remember, the spacing between two adjacent symbols was 2 times C. Okay, like this. And so forth. Okay, So if we have a constellation that looks like this, and we have in total m points here, this is the final expression. And this is where we actually ended in the last lecture. So what we would do now is to take this result further and plot it and compare and see what happens and so forth. And then we will also go into something called Emery QAM, which is actually a more used type of modulation than Emery PAM, or more used. Both are used, but this one is particularly important for radio transmission. So we don't go through this right now. We'll actually go through the derivation a little bit quickly. So never mind this at the moment. Go through this in a moment. Now, what we would like to have in a system, except for low error rates, we also want to have a high spectral efficiency. And the spectral efficiency nu is measured as the ratio between the bit rate that we can achieve and the bandwidth we need for the transmitted signal. And it's measured in bits per second per hertz. And this one is then limited by the Nyquist criterion. So we know that, forget about that. The Nyquist criterion comes into this, but it also the number of bits we have per symbol comes into this. And this one we will talk about in a second. So let's go on. So if we want to compare different physical layers, this is one way of doing it. We plot the symbol error probability along this axis as a function of something which is proportional to the transmit power. And in this case, it's ES over N naught. Okay. So this is when the symbol rate is fixed, which is then, okay, if the symbol rate is fixed, then this is proportional to the transmit power. This is sometimes called the SNR or the SNR per symbol. Okay. Okay. So anyways, we have the SNR per symbol here in dB scale. So this is a logarithmic scale. And we plot the error probability also in logarithmic scale. So this is sort of like a log-log scale. And then for different m's here, we get different curves. So for m equals 2, the error probability decays like this. For m equals 4, it decays like this. M equals 8, 16, and 32, and so forth. Okay. So when we increase m, what is good with this? Well, the data rate increases. For the same symbol rate, we said we fixed the symbol rate. The more m we have, the more bits per symbol we have, the higher the data rate. And the higher the spectral efficiency. So spectral efficiency increases like this. Better spectral efficiency. Yes, efficiency, okay, like this. However, the problem is that if we would like to reach a certain error probability, say 10 to the minus 2, which is not a very, I mean, that means 1% error, we can read off how much symbol energy we need in order to sustain this, and we see that we can get different requirements on the symbol rate energy, the symbol energy, or SNR, for different modulation schemes. So we get better spectral efficiency as we move here, but we get worse power efficiency as we go here. We need to invest more power to reach the same error probability. Okay, so along this range here is worse. I just write PE here for power efficiency. Okay, so we can increase spectral efficiency at the price of worse power efficiency. We can increase power efficiency, but only if we sacrifice in spectral efficiency. So spectral efficiency, power efficiency, like this, right? They can be traded against each other, but you cannot improve both at the same time. Right? At least if you use an optimal system, then there is always this trade-off. Any questions on this? Okay. And then to just quantify how much it costs in power efficiency to increase spectral efficiency, one can look at how many dBs differences there are between two of these lines. And it's about 6 dB difference. If we go a horizontal line, it's about 6 dB as we go from 4 to 8, and from 8 to 16, and from 2 to 4, and so forth. Okay, 6 dB, what is that? What does that mean? Well, first of all, if we go from here to here, we go from m equals 4 to m equals 8. So how many bits differences are there between these two constellations? We have 4 signal alternatives that corresponds to 2 bits, right? If we have 8, it corresponds to 3 bits. So there is 1 bit of difference between these steps here. And each such extra bit costs us 6 decibels in power. And 6 decibels, 6 dB, this is advanced mathematics, it's 3 plus 3 dB, right? Okay, and 3 dB is a factor of 2. So this is another factor of 2. So in total, another factor of 2. In total, a factor of 4. So we need 4 times as much power here as here. And that's substantial, right? So it costs a lot in power to get extra spectral efficiency. 1 extra bit per second per hertz costs us about 4 times as much transmit power as we started with. Questions? Okay. So which one should we choose? Well, it depends. You know, do we have power? Do we don't have power? What is our requirement on error probability and so forth? So none of these, all of these are used in real systems. Okay, error probability for QAM. So what is QAM? Well, basically it's like 2 PAM systems running in parallel, one along a cosine carrier and one along a sine carrier. And it has a constellation that looks something like this. Okay, so for different points here, that means a different PAM system along the in-phase axis here, cosine carrier, and something along the sine carrier. So to get the right decision in this case, okay, so suppose we transmitted this symbol here. Then the decision region for that symbol would be something which is divided along the I-axis like this. Okay. The decision region has to be to the right of this boundary and to the left of this boundary. Then we write in that dimension. And then it needs to be above this line and below this line in the other direction. So the decision region for this signaling point is here. Okay. So when do we make a right decision? Well, we make a right decision if we don't go too much to the left or to the right, and we don't go too much up and down. Left-right is a pulse amplitude modulated scheme along the I-axis. Up and down is a pulse amplitude modulated system along this Q-axis. So to get the right decision, we need to make 2 right decisions, one along each axis. Okay. So that's the key observation here. And then we can reuse our previous equations we had for the PAM system to construct the error probability for the QAM system. So I'll skip the details here a little bit, but if we're interested in knowing the probability of correct decision here, which is 1 minus the probability of making a wrong decision, we need to make a correct decision for the PAM system in the, along the horizontal axis and along the vertical axis. And since the noise is independent in this direction and that direction, I haven't really shown it, but you have to believe me on this, it is, then we can find this as the product of the probabilities for making a correct decision along the I-axis and along the Q-axis. And then it's just algebra to get to the final result. So I will skip this and then skip a few things, and then here is the final equation for this. Okay, so it's still Q functions. There is M, the number of signaling point, Mi, the number of points along the horizontal axis, and Mq, the number of points along the vertical axis, and M, the total number of points here, is the product of this, Mi times Mq, like this. And then, so that's the factor in front of here. Inside we have a Q function, a square root. We have ES over N naught here again. And then something that multiplies ES over N naught. And it's 6 divided by Mi squared, Mq squared, minus 2. It just happens to be like this. Okay, so let's compare then pulse amplitude modulation and quadrature amplitude modulation and see which one is the best. Okay, and then we get curves like this. So if you look at this, we have blue curves, which are for pulse amplitude modulation, and we have red curves for QAM. And we have the 64 PAM here and the 64 QAM here. We have the 16 PAM here and 16 QAM here, and so forth. So which system is best here? Let's compare them with the same spectral efficiency, say. So comparing, say, 16-nary systems. So this is QAM and this is PAM. Which one would you choose? How many for PAM? How many for QAM? Yeah, it's a slight overweight of QAM. Yeah, QAM is much better. I mean, it's actually said here also, so yeah, okay. No, the thing is that you would like to reach the same error probability, say 10 to the minus 2, at the lowest possible SNR. So if we compare 16 QAM, we need an SNR here, which is a little bit more than 15. I'm not sure exactly what it is. And then if we take that for PAM here, we need this SNR. And as it turns out, that could be, here there's a substantial difference between this. And as a matter of fact, if one looks at the difference between two QAM curves here, we get, there is a 6 dB difference between these two curves, but there are actually, in this case, 2 bits difference between these two curves. So for each 6 dB of extra power, we can get 2 bits extra in spectral efficiency. So QAM is much better in that respect. And that's one of the reasons why it's used heavily in radio, for instance. Any questions? No. Okay. So I know this goes a little bit fast, but you can look through these slides, and if you have questions, please come and ask me. I'll be happy to explain this in more detail. Now, we started this lecture by talking about symbol errors and bit errors. So both of them are interesting, sometimes in different contexts, and somehow they're related also. So let's discuss how they are related. What would you think, on a particular link, what will be the highest, the symbol error probability or the bit error probability? Any guesses? I mean, it's probably on the slide, but if you think about it first, what would you think?
I mean, if we have multiple bits per symbol, then the symbol error rate should be higher.
Very good. Excellent. Excellent.
It's
Very good. This is exactly it. So suppose we transmit 4 bits per symbol. I get a symbol error as soon as at least one of them is in error. But suppose that this bit is in error, then the other 3 are correct. Okay. So for a symbol error, we don't get necessarily 4 bit errors, we get maybe just 1. So in this case, only 1 out of 4 bits are in error per symbol error, and the bit error probability is only 1/4 of the symbol error probability. Okay. It could be also that all the bits are wrong, but that's just one possibility out of many. So to formalize these ideas a little bit, is that there is no, for a particular modulation and format, there is a relationship with the bit error probability and symbol error probability. It can be computed. It's a little bit complicated. But we can also bound it. We know in what limits these systems, how they related the symbol error probability and bit error probability for any system. So let's go through that instead of having special cases here. So if we have an M-ary modulation format with m equals 2 to the power of k, so k is the number of bits per symbol, then each symbol error leads to at least 1 bit error, but at most k bit errors. So something in between. So if I have 4 bits, a symbol error means at least 1 is wrong, 1 of the bits are wrong, and at most 4. Okay. In the extreme case, when all bits are wrong for all types of symbol errors, then the bit error rate is equal to the symbol error rate. Okay. So as long as we make a symbol error, then all the bits are wrong. And then if you think a little bit about it, it means that the probability that the bit is wrong is equal to the probability that the symbol is wrong. Now in the other extreme case, when only 1 bit error occurs for the symbol errors, then k minus 1 bits are actually correct. So it means that the bit error probability is only 1 over k times the symbol error rate. Okay. So this is the best it can be from a bit error probability point of view. I mean, let's say that symbol error rate is something, right? We keep that fixed. So this is the best bit error probability we can hope for, and this is the worst. And in practice, the bit error probability goes between these two limits. Okay. And we don't need to make more accurate calculations than this in many cases. But of course, we would like that the bit error probability tends to the lower limit, right? If we can make some design choices in order for this to happen. And as a matter of fact, there is one design choice we can do, and that is how to label the signaling point with bit patterns. Okay, so let's look at that. Formal proof here if you're interested. I will skip that. So for these PAM and QAM constellation, the most common way to label the constellation with bit patterns is using something called a gray code. And the reason for this is that the most and what is a gray code? A gray code is a code where adjacent symbols differs only, the bit patterns corresponding to adjacent symbols only differs in one position. Okay, it's probably easiest to look at this. Now, suppose we have a signaling point that we label with 0, 0, 0. The next point we label with 0, 0, 1. They differ in 1 bit position, right? And then we continue and 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, 0. And you see, they only differ between 1 bit as we go 1 step, right? Adjacent points only differ in 1 bit position. And this in contrast to something called the NBC code, or the natural binary code, which is, you know, how you would, this would be 0, 1, 2, 3, 4, 5, 6, and 7 in binary format. That's why it's called natural binary codes. But here you see, here there is a difference in the beginning between here, 1 bit, 2 bits. See that? 1 bit, 3 bits. That's a really bad transition here. And then 1 bit, 1 bit, 2 bits, and then 1 bit. And the reason why it's these transitions here from, say, let's see, let's pick the particular bad one. Okay, from here to here, there's 3 bits that differ. You see that? And the reason why this is bad, because if we transmit this point, the most likely symbol errors is to adjacent points. So up here and down here. And when we make this type of symbol error, all our 3 bits are wrong. Okay. While in the gray code, if you go to an adjacent, only 1 bit is in error. Okay. So with gray codes, we tend, for high SNR, that the bit error probability tends to the lower limit. Okay. So that's why these gray codes are used in practical systems. Okay. So the upshot here is that the bit error probability is roughly equal to the symbol error probability, and then 1 over log 2 of m, which is, of course, 1 over k PE, if you like. Okay, questions on this? Right. So in the project, you will be asked to build a pulse amplitude modulation scheme that reaches a certain bit error probability. And maybe now you got a few hints on how to label your symbol points, right? Okay. If one wants to do this in 2 dimensions, it's easy to do that. One simply has a gray code along one dimension and a gray code along another dimension, and then one can show that it is a gray code in the sense that if I take a point here and I go up, right, down, or left, only 1 bit swaps. You see that, right? And as a matter of fact, this is how the Wi-Fi constellation is labeled, exactly like this. Okay? Any questions on the physical layer now before we move on to the next phase here? Yes?
You don't have to use gray code for 4-PAM or 4-QAM, right?
Yeah, I mean, you can, let's see now, 4-PAM, then you have 2 bits. Yeah, so you can use a really bad constellation that do this, right? And 1, 0, and 0, 1. So yeah, you use a gray code for that also, for 4-PAM. For 2 binary, it doesn't matter, of course. But for all others, you can use a gray code. And there are gray codes for any constellation with a fixed number of bits. So from 1 bit, 2 bits, 3 bits, and so forth, up to infinity.
Okay.
Yeah, so it's easily constructed. And it works in 2 dimensions also. Okay, any other questions? I don't know what's going on. I prefer not to know. Okay, so then if we go on to the next part here. I know I promised that the physical layer stuff we did last lecture was the most challenging from a theoretical point of view. This is also a little bit of a challenge. One can make this coding theory quite advanced. So we will try to cut a few corners and try to convey the basic information around this. But there's many things under the hood. But I will try to make it understandable without being uninformative. Okay, so with that little bit of excuse, let's get going here. So we will talk about something called binary block codes. And what is that? Well, it's one of these boxes that accepts bits coming in and bits coming out. That's why it's called binary. And it's called block because we accept a block of input bits and produce a block of output bits. And if you see here, we have k bits coming coming in, and we have n bits coming out. And such an encoder is called an NK block encoder. So n is the number of output bits, k is the number of input bits. Okay, so the input bits, these bits are called the data bits or information bits. The output bits here are called code bits. The block of information bits is called the information word, the data word, information block. Same thing. Okay, so it's a binary k-bit, k-element vector. So it's a vector of k binary numbers. Okay, the code word is what we get out, and that's a binary vector, 0, 1, and has n elements. So it's an n-element binary vector. The code is the possible outputs. So how many outputs can we have? Well, how many inputs can we have? Possible different inputs. We have k bits. How many inputs do we have? 2, because it's binary, and k, right? 2 to the power k. These are the number of possible inputs. And since the block encoder here is just a translation device, the number of outputs is also 2 to the power of k. Okay, and we can put all the possible outputs into a set, and that is what's known as the code or the code book. The code rate is the ratio between the number of input bits to the output bits. And the number of output bits, n here, is always greater than k for any practical block encoder. It could be equal to k also, but that's not super interesting. It cannot be less, because then we throw away information bits, and that's typically not in our interest. Okay, so we don't do that. So n is greater than k, so this code rate, which is k divided by n, is a number which is less or equal to 1. And the code rate tells us how many information bits there are per coded bit. And the code rate tells us a little bit of the efficiency of this code, because of course the extra bits we add to this are more bits that we would like, that we need to transmit, and we would like that's going to cost in power or bandwidth or a combination of these two things. So for efficiency reasons, do we want a high code rate or a low code rate? Here I actually will wait for an answer. So.
Did you say for efficiency?
For efficiency reasons.
Well, that would like k and
Yeah?
so you want it to be close to 1?
Yeah, exactly. So we want a high code rate, because that means that we don't add so many extra bits here, overhead bits. Okay, and we'll see more about how this comes into play a little bit later. So for efficiency reason, we want the code to be high, but then we also want the code to do its job, which we haven't discussed yet. And you could guess what that means. That typically means that the code rate needs to be relatively small, right? If it's smaller, it can be better, but then it costs us in efficiency. Okay. And then finally, we would discuss codes in this class that are linear. And linear codes are such that the linear combination of code words is also a code word. So what does that really mean? Well, it means the following, that if you give me a code word, or two code words, one, say, let's call it CK, and another code word, let's call it CL, then I know that CK plus CL, the result of that will also be a code word. Okay, so CK plus CL will be some binary pattern CL, and this will be also in the code. Okay, and this circle plus means binary addition, so XOR if you like. You remember this, right? 0 plus 0 is equal to 0. Oh no. And then 0 plus 1 is 1. 1 plus 0 is 1. And the only thing which is surprising here is that 1 plus 1 is 0. Right, exactly. Okay. And this interesting fact is that addition is equal to subtraction. Right, so 1 plus 1 is 0. Okay, well, anyways. So let's look at one example of such a block code. Okay, so we have an input word here, and say that we have a 2-bit input. So 0, 0, 0, 1, 1, 0, and 1, 1. And then we have 4 bits out. So the code words corresponding to this could be like 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, and 1, 1, 1, 1. Okay. So what is n here, and what is k? I know it's Friday afternoon, right? But so k is the number of input bits. So thank you. K is equal to 2. What is n? And 2, 3, 4. Man, come on, guys. So the rate is 1/2. Okay. So the rate 1/2 means that on the average, for each code bit, there is half an information bit in it. Okay. Okay. Good. So now we will specialize this. We will talk about linear block codes. And yeah, by the way, is this a linear block code? This is a tough question, actually, so I'm not expecting an answer. But linearity, how do we check for linearity? Well, it's basically that if I take 2 of these code words, any pair of 2 code words, and I add them together, I should get another code word. Okay, so 0, I can add that to any of these code words, and it becomes the same, right? So adding 0 is easy. It doesn't change anything. Otherwise, if I add this one and this one, that means that I take the XOR of everything, and you see that we get what, if we take this plus this, what do I get?
The last one?
Exactly, the all one pattern, right? So the 0, 0, 0, 1, 1, 0 becomes 1, 1, like this. So if we put up here, we have the first code word, C1, here. Let's do 1, 2, 3, 4 like this. I can get to C3, for instance, by simply adding C3 to this, like this. And then I can go to C2 by simply adding C2 to this. So we think of these as being vectors, maybe. So this is the origin. I go like this, I get to C3. I go like this, I get to C2. And then if I go across here, C4, then we get this point like this. Okay. Now, the interesting thing here is that if I go from C3 to C4, the vector which is missing here is actually C2. If we write this out, C3 is 1, 0, 0, 1, like this. C2 is what? 0, 1, 1, 0. And C4, we see that that's this vector plus this vector. So it's C3 plus C2. And one can complete this by adding the missing links like this. So it turns out that C4 brings us across, C2 brings us down, C3 brings us to the right. But since everything is symmetric, it also brings us the other way. So if I take C4 plus C3, I get C2. Okay. So yeah, so this is a linear code. Okay. And linear block codes are by far the most used in practice. So this is not a uninteresting special example. Okay, special case. So systematic block codes is a special case of block codes where the code words have a certain structure. And it works like this. So the input is still D and the output is C. But the output, the code word, copies the input as the first k bits and then adds some extra bits on top of that, to that. So D here is our k bits, input bits, and P is our n minus k parity bits as they are known. Okay. So the code word consists of the input plus some check bits or parity bits. We have k input bits, and therefore we have n minus k parity bits, like this. Okay. Is this a systematic code? No? I hope it is. Okay, so the thing is that if we look at these bits, these are the input bits, we will find them exactly here, right? You see that? So this is the systematic code, where the input, in this case the two input bits, are the first two bits of the code word. So yeah, this is a systematic code. So this code, this mapping that I just invented had these two nice properties. It's linear and it's also systematic. And systematic block codes are used heavily in practice. I think the majority of the codes used in practice are both linear and systematic. Okay, so this is important special cases. Okay, so I'll think we'll take a break, 15 minutes.